Hello, and welcome to 5-Minute Math. Today we are looking at the Algebra 1 concept of interpreting exponential functions. This is standard A.9B in the great state of Texas, and we are using item number 46 of the 2018 released STAAR test. If you haven't done so already, please go ahead and take a moment to pause the video, work this problem out on your own, unpause it, and we will look at our answers together. So we've got scientists studying bacteria samples, and we've got this function here. It's an exponential function giving the number of the bacteria at the sample at the end of X days. So we're going to see bacteria samples. We're going to see any type of population growth or compound interest. Those are two typical ways we would see exponential functions in the real world. So in this case, we've got population growth here, and we just need to interpret one of the values in the function. All right, well, we've got three values, so let's break each of them down here. So our exponential functions typically take this form: y equals a times b to the x power. Seems pretty simple, but you'll notice there's going to be a slight difference here. This a is a constant because it's just multiplying by whatever b to the x power is, but it's not necessarily changing. So we're going to look for an item or a term that is not necessarily changing. So typically you might see this as a starting amount, simply because the starting amount is not going to change as long as they don't introduce any new bacteria or take away any new bacteria. That constant right there is typically going to be your starting amount. Then you've got this b right here. Okay, so this is the one that is going to be multiplied or by the x power right there. And so this is typically going to be a rate. So it's going to be a growth rate. It's going to be a decay rate, depending on whether the population's growing or getting smaller. But what we're typically going to do there is we are going to add 1 plus the actual rate. Because if we just put the rate, let's say it's a 15% growth, we just multiply it by 0.15, you're going to just get the amount that was increased, but you lose the initial amount. This 1 right here keeps the starting amount in there, and then adding the rate on top of it just multiplies over that, so you get a nice neat number at the end that shows the new population rather than having to add the original population in afterwards. And then the x is typically a time period. So days, weeks, months. And so on population growth here, we are going to say, it doubles by, it doubles every 3 days, or it grows by 15% every 2 years, or something like that. So let's take a look at what we have here. So we've got 245 times 1.12 to the x power. Okay, so let's see. The initial number of bacteria is 12. Well, I see the 12 right there, but the initial number of bacteria, remember that 245 is our constant. It's typically our starting amount. So we would say 245. So the initial number is going to be that constant, that 245. It's not going to be 12. So G. The initial number of bacteria decreases at a rate of 88%. Now, where do we get the 88 from? Well, if you take 100, take away 12, right? We've got that 12 sitting right there. You get 88. But this is not, we're not decreasing, we're actually increasing. It's 1 plus the 12. So it increases at a rate of 12%. I know it's 12%. Because it's that 1 plus that 12. So I take that 1 away, that 112, take away that 1, and you're going to get your rate increase, 0.12, which is exactly what we have here in H, so that looks good. Let's check J. The number of bacteria at the end of 1 day is 248. Nope, that's the starting amount. The starting amount is 245, not the ending. So our answer here is H.